السلام عليكم.
وعليكم السلام. السلام.
Inshallah, today we'll cover two very important topics. We're going to talk about the classification part of the computer-aided diagnostic system, and then we're going to start from code that we did last time and basically complete our first CAD system with the classification and also performance measurements. So basically, if you have any question from last time, please let us start with the questions from last time. Have any questions from last time?
Doctor, actually, I have some questions about the research.
Go ahead.
Just if you give us a quick explanations for the section A and the F.
You're talking about the research problem itself?
Yes, the section A and section F of the research.
Actually, I'm going to explain. Basically, these are not the parts that you're going to do. Basically, I'm going to send you an assignment, and these are very general. But let's talk about what you have also. A second, I'll share it. So you're talking about section A. Section A. A and F. Can you see it now? Basically, what we're going to do is data. Basically, just the division of the mammography data into training and testing. This will be the manipulation that we're going to do. When we get started, probably going to be next time. Basically, we have to resize the images to match the input to the neural network. So basically, these are so this is for A. Basically, we're going to see these either today or next time, inshallah. F, basically, these are the accuracy, to predictive value. These are the kind of things that we're going to use as evaluation for different systems. These are not the questions that you're going to answer. Basically, I'm going to send you assignment. Basically, this is one thing that I was going to talk about at the end of this lecture. I'm going to post an assignment that is particularly dedicated to the first part of, or the statistical classification part of this research problem. It's going to be like, it's very likely that we're going to have two assignments also for research problem 2. One of them deals with the classification system that we okay, in these assignments, I'm going to detail whatever I'm asking you to do. Okay? So please don't worry about these are just general topics.
Yes.
Do you have any other questions?
Sir, I have a question. The last question.
What is this?
The last one. This one here?
I have a question.
The last lecture? The code? The code?
The code.
Yes, this is the code right there. Can you see it?
Yes. Doctor, but I can't. Uniformity. Can you look as an example? I can't do it.
Is it here in this code?
No, not here.
But actually, it might be because of the version of MATLAB. So basically, you need to take it into account the MATLAB version in order for you to be able to use it. Sometimes the code I post in an earlier version of MATLAB. So basically, if you want, I'll send the code that works with MATLAB version 2028.
Okay, inshallah.
Okay. So today, what basically the classification part. I'm going to talk about aspects of classification, and then basically we're going to go ahead and modify our system to include the classification part. Basically, the classification or the classification part of our system, basically the training data, and basically the testing data what we need to input basically for this simulation, the classifier give us the basically predictions or predicted outcome. Of cases where I know exactly, basically I have, for example, 10 normal, abnormal cases. Okay, the will be basically these are data. Okay, what I do is basically how to classify the. I take these and compute the features. Do the feature fraction. Space data. Here, what we have here is image space data. What we have here are ROI. After we do these steps, basically we will have here the same number of cases, but instead of having for each one of them an ROI, no, I'm going to have a set of features. What we did last time was to build a feature extraction system that basically ended up giving us, let us run it and see, I don't remember how many features we ended up having. We can run it and see. This is exactly the same code that we used last time. Basically, at the end, what we had was, we have 72 cases. We had 7 features, 7 useful features at the end. Okay, so basically, if we have 7 features at the end, this means that we have basically for each one of the cases, we have only 7 numbers. Instead of having an ROI of 32 by 32, we basically summarized the 32 by 32 into just 7 numbers. Okay, so the classifier, the basic function of the classifier is that basically in the feature space, basically it's something like this here, like the figure that we have here. Okay, we have the feature space looks like this. We have the blue X's and the red circles, and each of them represent a different class. Basically, the function of the classifier is to try to find a surface, some kind of a surface. This surface can be a line if it's two-dimensional. It can be a plane if it's three-dimensional. It can be something like a surface, like a curved surface, like a parabola or paraboloid or hyperparaboloid if you have multi-dimensional space. At the end, we define a certain surface that separates these two from each other. Okay, so for example, if we have only two-dimensional space, basically we're going to end up having in the two-dimensional space, basically we have, this is one dimension, this is the second dimension. Basically we have circles and X's, okay? Like this, for example, okay? Have circles like this. Okay, for example, okay? 3, 7, 3, 7, need another one. Okay, like this, for example, okay? These are, for example, these are my data, basically. This is a class, this is class 1. And the circles are class 2. And I need to have basically a classifier that can distinguish between these two classes. So basically, this surface, in this case, if I try to make it a line, okay, basically it can be like what? Like, for example, if I have a line that looks like this, how about that? Would it separate them? Does it have a problem here, right? Can you see it? It's not going to be accurate because of this one here. How about if we make it something that looks like a curve? If we have something that looks like, for example, like this. How about that? Would it separate it? Would it be able to separate this? Let me draw it a little bit in a different color. Basically, the first line looked like this. It had an error here. This was not correct, right? This was not correct. If we take another line, or if you take a curve, it would look like this, for example. Which one of these is better? Your opinion. Both of them have one incorrect. Which one of these is better?
First
okay,
one.
Yes, go ahead. Go ahead.
First one, because it's simpler than the second one.
It is simpler. Okay, that's a good way of looking at it. This is definitely an answer. Some people actually think that the distribution here would actually better fit something that looks like this. So basically, for the few data points that we have, they actually both have one incorrect data point. Okay, so they are basically, if you try to use any metric, they will be basically equivalent. Basically, the error rate will be exactly the same between these two. How about if we come down and basically try something that's a little bit different, like this? I have a surface that looks like, let me try a different color. Okay, maybe this one. If I try a surface that looks like this, would that be better? How about this surface here? This has 100% accuracy for training data. Is that better? Do you think this is better?
For the accuracy, maybe. Okay,
this is one very important thing that I would like you to observe from the beginning. Basically, if your curve basically has so many curves like this. Basically, this is basically the first one here. Basically, was a first order curve, right? This one here looks like a parabola, so basically it is likely to be what? Second order. Maybe I should write it like the first one. Second order curve. The third one here, actually, it looks a little bit higher order. What is the meaning of order? The order here means that if I have to write an equation for the surface, basically for the first one, it's going to be like this. Y is equal to ax plus b. For the second one, it's going to be y2 is equal to ax squared z plus bx plus c. It's going to be like a second order curve. The third one is likely to have a little bit higher order. It's going to be like ax to the power 5, for example, plus b x to the power 4 plus so on and so forth until you have at the end whatever, d or whatever, okay? C, d, whatever, e, okay? So basically here you have two parameters to estimate. Here you have three parameters to estimate. Here you're going to have basically the number of parameters is equal to the order plus 1. So basically here is going to be you have 6 parameters to estimate. So it appears that if we increase the order, basically we're going to have to estimate more parameters in order for us to be able to fit it properly. The problem is most realistic curves, most realistic problems will not have a classification surface that looks like this. So basically the higher order surface is very unlikely to be correct, very unlikely. It actually gives you something called overfitting. This is a very big word. This is one of the key words, a very famous word in the field of classification. And this is a big problem. This is a major problem. Why is it a major problem? It is a major problem because your model will fit the training data perfectly, but unable to perform well with testing data. Why is that? Basically, you usually have, if you look at the data here, you would notice immediately that probably this point here looks like a little bit of an outlier. It's very different from the other points. Here, probably this point is okay, actually, if you consider this curve right there, but actually it's not a good idea to try to fit every single point in the training curve. If you're going to have a higher order curve for classification, you're going to make sure, you have to make sure that you have so many data points to be able to verify that this is actually correct. If you don't do that, it's very likely that you're going to end up with a classifier that you trained with your data and think that it will work perfectly, and it ends up basically performing very poorly in the field when you try actual testing data. So let me give you another example. Maybe consider something that is a little bit clearer than the example that I just gave you. Basically, let's just consider that we have data points that look like this. And basically, we have data points that look like this. Okay. If you try to use an overfitted model, basically the model will try to do the following. Basically, the classification surface might look like this. Basically, you want to keep this. You want to keep the circles up and the axis down. Okay. This will be a surface that will give you 100% classification for the training data, but realistically, it will be outperformed. It's very likely to be outperformed by a curve that looks exactly like this. If you use a classifier that looks like this, just a simple line, basically, with the circles up and most of the circles up and most of the axes down, this would be much better than the curve that basically goes up and down like this one. So basically, this one here is an example of overfitting. Okay, this one here is very likely to perform much better in the reality with testing data, because basically sometimes noise will basically cause these variations around the classification surface. But you can see very clearly that most of the circles up and most of the axes down. So basically this seems like a very good classification surface. So basically this is the first example. Second example, it looks like this. Basically, you might say also that I'm going to use a surface that looks like this so that I don't have any overfitting. So basically, I would come and basically put my classification surface like this. Actually, you might notice that if I took a surface that looks like this, this is like a parabola. This is a second order curve. So basically, this is second order. This is, of course, first order. Basically, what you're going to have here, if you have a parabola here, you get much better classification than the line here. And basically, the line here, if you just consider this line here, this will be called underfitting. Underfitting means that you basically simplified your classification problem with a very low order classification surface and ended up basically losing performance because of that. Second order is really good. Second order is not basically, you cannot consider it like the overfitting. It's not going to basically cause you the overfitting problem. When you have curvature, so many curvature like this is overfitting basically. I can assure you that if you design your system to work like this, you use a model with so many parameters that fitted every single point in the training data, it's very likely that it will perform very poorly in the testing data. Here, if you use a surface that looks like a second order surface, and you see that the second order surface performed much better than the first order, it would be actually likely that this would perform better than the other line, the single line here. And basically the underline, if you use it, it would be called underfitting, basically using a model that has lower parameters or lower order than what you need. So overfitting model with too many parameters. Underfitting model with too few parameters. Okay, so highlight the the keyword in each, too few and too many. And basically these we're going to see actually, because when you try a particular system, we're going to try classifiers today, you'll be surprised that you train your classifier and basically some classifiers perform really well, some others perform not as well. And the cause of that will be related to the overfitting or underfitting problem. The different classifiers assume different models. And basically, what we have to do is basically do experimentation. It's extremely difficult to know ahead of time if you have your data, for example, like the features that we extracted, even though they are only 7, it's very difficult to know if we're going to need a first order or a second order classification surface just by looking at the data. It's extremely difficult. Okay, what we saw, the curve that we saw here, this was actually one dimension. These are the number of cases, and basically these are the values. So basically these are not even 2-dimensional. Imagine that you're going to put each one of these as a dimension, each one of the points that you have as a dimension. You have 7 points, and basically imagine that you have a 7-dimensional space. Imagine further that usually if you're designing a computer-aided diagnostic system for something as important as mammography, you're going to probably end up with maybe 300, 400, maybe more features. Okay, then you're going to design the classification surface out of these. So basically, you have a very high dimensional space. It is extremely difficult to visualize the data in that high dimensional space. So it's extremely difficult to know if this is if the particular model will fit or not. You have to try it. You have to actually implement the classifier and use it, and then use the performance metrics to know if the model is sufficient or not. I'm just giving you ideas about why a model, why a classifier. If you train a classifier, why would it perform poorly? If you have a classifier that was overfitted or underfitted, you're likely to have a problem with the outcome using the testing data. Okay, is that clear? Okay, so basically this is very, very, very important. Okay, let's start with the classification of classifiers. Okay, there are different classifiers that are basically different techniques of classification. Something called parametric classification, and another called nonparametric. Parametric classifiers basically like the ones that we have been talking about so far. Basically, if I'm going to have my classification surface as a curve and then estimate its parameters, then basically this is a parametric classifier. For example, let's see the equation that we have here. We have here 2 parameters. For the first one here, we have 2 parameters, A and B. And I use the data that I have, the training data, to estimate A and B. Once I estimated A and B, that optimizes the outcome, basically I don't need the data anymore. Okay? If I design this curve here, then why do I need the data for? I don't need the data. So the training data is basically used to estimate the parameters of the model. This is called the model, classifier model. Okay. Once you design the classifier model, you don't need the data anymore for the parametric classification. Okay. So basically, any classifier basically that does that, basically the data is used to predict the model. And that's it. For the non-parametric, we don't have a model. We just use the data. Basically, we call this model free. Which one would be better, in your opinion? Is it better to use a parametric or a non-parametric model for classification? Basically, Yeah, go ahead. Go ahead.
Maybe parametric.
Actually, if you're using the right model and using your data to estimate the right model, definitely the parametric would be better. Unfortunately, as I was just saying, sometimes the model is not accurate, is not suitable. Okay, so basically, if you have, for example, let me give you some example for the failure of the parametric model. If I have data that look like this, okay, and the circles are all around it. Can you design a surface that looks like a circle around it? So can I design a classifier? If I use one of the parametric models that I was just talking about, would it be possible to design a surface that looks like this? It's extremely difficult. Okay. If you're trying to use, for example, a first order model, if you're trying to use a first order model, just classify this, will it be okay? Definitely not. You're not going to be able to find a line that will give you any good results. One of the famous problems is the exclusive OR problem. If you have 2 points, maybe I should draw it in the right colors. Of the very famous problem, what's called exclusive OR problem. I have my data point looking like this. How about this? Can you find any first order, any line that would separate the X's and the O's? Impossible, right? This is called exclusive OR problem. You have your data like this. It's extremely difficult. You cannot do that. So if you use a parametric model with the incorrect model, you're not going to be able to do any better than the nonparametric. The nonparametric actually don't need anything. You basically have the data. The simplest of these, the nonparametric, which is going to be actually very interesting. You're going to find out that it's one of the best classifiers, even though it's one of the simplest. Basically, if I have my data looking like the example that I just showed here, okay? And if I have a data point that is, for example, let me put it as a star here, okay? How would you classify this if you have the data points like this? Basically, I don't have a model. Basically, I have the data, okay? And I have, this is my test case. How do I classify the test case in your opinion? Just give me the simplest answer that comes to your mind.
Comparison between
Yes,
other comparison between other data.
Yes. How would you compare them? For example, let me if you compare them, would you classify it as red or blue? Let me give you another test case. If I have a test case here, maybe I should put it here, for example. Another test case. How would you classify test 1 and test 2? Let me give you an example from reality, okay? Imagine that a patient, when he has a high temperature, he has, for example, stomach ache, and basically unable to basically walk, for example. He was classified, he went to a doctor, and basically this doctor told him that you have this particular disease. Someone else had high temperature. He didn't have stomach ache, but he was unable to walk as well. Would you classify him to be exactly the same diagnosis as the first one or not? Let me put it in another way. I have patient 1 and patient 2. Or just patient 2. Okay. You have the patient, okay, and have disease 1 and disease 2. Okay. You have certain criteria for the disease. Okay. You have criteria A, B, C, and D. Okay. For disease 1, this is okay, this is okay, this is not okay, this is okay. For disease 2, this is this is okay, this is okay, this is not okay, this is not okay. The patient, basically, that you have has all of them. Which one of these diseases would be the correct diagnosis for this patient, in your opinion? And how do you reach a decision here? First of all, by the way, when you go to the doctor, usually it's almost impossible for the patient to present exactly the symptoms for a particular disease. Basically, usually you have a variation between different patients. So basically, some patients might complain from something extra. Some patients might complain from something less, okay? Might not complain about something, okay? Based from the basic criteria for the disease. But what should the doctor do? He basically approximates, basically. If you look at the comparison between the patient symptoms here and the disease one, you'll find that you have only one difference, right? If you compare it to disease 2, what do you see? You have two differences, actually. So which one should I basically consider the patient to belong to? Which one of these will be a closer disease to what he has?
Disease 1.
Disease 1, right. Let's see exactly what we have here. Basically, these are the feature space points. This means that if my case here is close in distance to a particular case, then it's likely to be exactly the same diagnosis. If you look at test 1, the distance to the closest X probably is going to be this distance here. The distance to the closest circle here will be this small. So which classification should I give to test 1? Red or blue?
Circle.
Right. Very much the same idea that we had in the patient disease classification. Here it's exactly the same. This is a test case here. This is the smallest distance to an X, and basically this is the smallest distance to a circle. This is much longer than this, so basically this will be basically blue. If you imagine that this is actually an idea for a classifier, a very famous classifier called K nearest neighbor. K nearest neighbor classifier. K is a number. You can make K equal to 1. If you have binary classification, usually you take K equal to an odd number. 5, so on and so forth. Basically, the idea of this very simple classifier is that I choose the closest K neighbors. Okay? Usually, if you have, for example, if you choose K equal to 3, okay? Basically, K equals to 1 is the nearest neighbor. Some people just call it nearest neighbor, not K nearest neighbor. Nearest neighbor. You just classify like what we did right now. Classify the test cases as the same diagnosis as the closest point to them. Now, more robust, if you have noise or something like that, usually it's better to have more points. Just pick the 3 closest neighbors, and then if you have, for example, if this is your case, and you have circles like this, this is a circle like this, and this, and this, and you have x's like this, just trying to make it make sense. Basically, maybe I should remove the last one. Basically, let's just look at, and basically, let's have another surface here. Okay, this is like a circle. Okay, imagine that this is, it doesn't look like a circle, but it should be like a circle. Okay, so basically, let's just remove this here, make it in the center so that it's clear. This is my point at the center. Okay, and make it like this. And basically, if I have and maybe I should have, if I have 5, so now if you consider only the nearest neighbor, okay, which point will be this best case classified to? If just one neighbor, this will be red, right? Because what? Because basically this is the closest one. If I choose the 3 closest neighbors, then it will be what? If I probably shouldn't have this one here. If I had the 3 closest neighbors, then I will have to include this. This one here, and this one here, and this one here. These are the closest 3. And if I have 3 neighbors, then I will classify it as blue. If I have 5, then I will have these, and will have also, maybe this extra point is not needed now. Then I will have these 3 and these 2, and basically if I have 5, then it will be classified as red again. So basically sometimes it depends on the kind of data that you have, and usually when you have data that is basically that is overlapping like this, the k-nearest neighbor is actually very good, because it can detect basically something that looks basically like this. Basically, if you have points that you have red points in the middle of blue ones, or if you have blue ones in the middle of red ones like this one here, it can actually perform much better than the parametric classification method. So basically what we have here is, all what we need to do is just keep the data, and whenever we have a new case, we just test the distance or choose the number of neighbors that basically that are equal to k, that is equal to k, and basically we see which class is dominant within that nearest neighbor. Okay, so basically sometimes they call it here, they add another word here, voting k nearest neighbor, meaning that for the 3 neighbors here, we do voting, and we choose the class of most votes. So if we have 1 neighbor, then there is no voting, basically, just basically the nearest neighbor. If we have 3 neighbors, then I vote amongst them and choose the class of most points and consider it to be the classification outcome of this case. So k-nearest neighbor, in spite of its simplicity, is very simple. But actually, it's one of the best classification methods that I've ever worked with. Actually, it's extremely efficient, it's extremely accurate, and basically it can adapt to any data model without having to specify parameters or anything like that. The point is the choice of this k here, we have to try it by experimentation. So usually I would try k nearest neighbor with k equals to 1, to 3, to 5. I usually choose an odd number, as I was telling you, because if I have a binary classification, you don't want to have k equals to 4 and you end up with 2 and 2. Okay, because it's voting. You have to actually be able to say that this one won, this particular class won. You don't want to have ties. You don't want to have basically equal number of points from the two classes, and so you're not going to be able to decide or make distinction between which one is better. Okay. So basically, for the parametric classification, we have to have a data model, and basically one of the most famous examples of this is actually called SVM, support vector machines. Okay, these are very important, and you will find them in most of the publications actually dealing with classification. We have to use it or have to try it amongst the classification methods that we use. And the non-parametric, actually, the k-nearest neighbor is basically the dominant one in the non-parametric case. What we need to do now is to get started and implement both. We already had features from last time, but we need to actually implement or add whatever is needed to be able to add the classification methods and also add the part about the performance metrics using the sensitivities, the specificity, and so on. We're going to compute the confusion matrix that we talked about, and then compute from it sensitivity and specificity and all the other things. What we had from last time, we took all the data that we had and computed the parameters. This is actually not correct. Okay. Basically, what we need to do, we cannot do that because even the selection of the features, we cannot do the selection of the features with the testing data. Testing data has to be, you have to keep it away from whatever you're going to do. The design of the features, how you're going to select them, the design of the classifier, and the learning phase of the classification that you're going to use. Basically, the testing data should never be used in that. So basically, what we need to do in order for us to be able to take our code and add the classification to it, basically the first step you have to divide the data you have into training or learning, whatever the name you want, and testing. And these two must be completely independent. You cannot use the testing data for anything related to training. You basically, the data that you have for testing should appear basically, you use it only as the input to the classifier to basically test the outcome of the classifier. Basically. You cannot use it for anything other than that. If you use the testing cases or the testing data to design which features are better or train the classifier in any way, then your system will be biased. Your system will be incorrect. Okay, it's like you're giving the students the final exam. Okay, if you do that, if you give them a part of the final exam, then this part of the final exam will not test their ability to understand the material. Basically, it's going to be basically something that will be almost guaranteed to be solved. Okay, so this is the first step. Usually people can do this division in different ways. Some people make it like 50-50. Some people do it like 70-30. You can do it in any way you want. Okay, actually the best way is to design your code in order for you to be able to change it, the way you want anytime. So basically, we're going to have this selection or this division as variable, and basically, when I put this as 0.5, for example, then it will automatically know that the other part will be 0.5. If I put it as 0.7, for example, basically everything changes to be 70-30. So this is the first part. So once we do that, we compute features, very much like what we did last time. We compute it for the training also and testing. We do it for both because basically I want to convert the image space into feature space. Okay, this has to be done for the training and testing. You cannot do it for the training only or the testing only. You have to do it for both. So if I'm going to compute or consider the feature space containing certain number of features, I have to convert my testing cases into that domain, into that feature. I have to compute the features for the testing. I'm not going to use them until I do the classification part. But basically, I have to compute them. So this is going to happen. This is going to have to be done in my code. And after we do the extraction, the feature extraction, basically we have to do the selection. We're going to do that with t-test, like what we did last time. But we use only the training data here. Basically, the testing data, you keep it away from what you're going to do here, because basically what you have, you just imagine that these cases are what you have. And you design based on what you have. You're not going to design based on the patient who's going to come when the system is complete. You're not going to do that. The patient who's going to come, when you actually deploy your system to the clinic, you're not going to be able to know exactly what his parameters are. So the selection will have to be done using the data that you have, which is the training data only, basically. This is what we did last time. Once we do that, we're going to do the classification. The training phase of the classifier is basically where the model is built. You build the model. Or basically, if you have the data, if you're going to use the nonparametric or data free or model free, basically you have to have the training so that you're going to be able to basically classify using the data itself. Okay, so basically the model is built here and use the training data plus their labels. You have to have labels for the training data. You already know that there are cases that are known to be normal and others that are abnormal. You're going to use these labels to be able to do the training. You're never going to be able to do a training without having labels, because basically you're going to present the features for a particular case, and in order for the classifier to use it or learn based on it, you have to give him also which case is that, which is this a normal case or an abnormal case. Testing phase after that will be basically we use the test data as inputs. And basically get the predictions. Okay, so is that enough? No, it's not enough. Basically, now we presented the data. Here, we didn't talk about labels for the testing data. We already have labels for testing data because basically all the data that we have 72 cases that are known to be normal and 72 cases that are known to be abnormal. But here for the testing, we just present features without presenting the actual labels. What we do in the last step, final step basically, is to do the performance metrics, performance assessment. Basically, we have the predictions, we have the labels for the testing data. Okay, so basically what we're going to do is to compare them. This is like what we had in the confusion matrix. We had the outcome, we had here the truth. We had here the predictions or the diagnosis, okay? Normal, normal, abnormal, abnormal. We basically predict these numbers, the 4 numbers in the confusion matrix. And based on these, we compute the performance measures for performance metrics, which are mainly sensitivity, specificity, accuracy, and so on. Like the predictive value, what's the predictive value? Okay, and based on these, we actually now we know the performance of the system. Basically, and we can basically try different classifiers, different sets of features, different feature selection methods, and look at the performance metrics. Performance metrics are realistic because basically we obtain them from a completely independent test data set. And basically you can compare different systems based on that. And the one that gives you the best performance metrics, this is the one that you're going to be basically saying that this is the best system that I found to give results to solve this particular computer-aided diagnostic problem. Okay. Do you have any questions about these steps? We already did some of these steps, but actually we have to do some of the division, which is basically the data manipulation that we talked about. We're going to have to compute the features after we did the division. Basically, you have to not just compute for the normal and abnormal, we have to compute for the normal, abnormal for the training, and normal, abnormal for the testing. The selection will remain exactly the same, but we're going to use only the features that were obtained from the training data. And basically, the classification part is the one that is really new. And basically, we're going to go to MATLAB help and see the function that we were talking about, the support vector machines and the k-nearest neighbor. We're going to start with the k-nearest neighbor because it's much simpler. But actually, what we're going to find out is that all the classification methods in MATLAB, they have almost the same code. You just use a particular function for the particular classifier. Whenever you want to build a model for SVM, there's a function to build the model for SVM. Whenever you want to use KNN, there is a function that builds the model for KNN. And the actual classification is using exactly the same function. So basically, you're going to be surprised that the classification part is going to be extremely simple. So if I wanted to use a particular classifier, it's probably going to be like a two lines of code. That's it. So do you have any questions about these steps? Any questions? Okay. One thing actually before we basically, I'm probably going to need some more time today. Going to need to basically, have at least an hour to do that. So what I suggest is when Maghrib prayer comes, basically we take a 15-minute break so that we pray, so that we don't delay the prayer at 6:30 or something like that, because now it's a little bit late to pray Maghrib at 6:30. And basically, if we take a break at 6 or something like that and pray and then come back for another 30 minutes, would that be okay with you?
Okay.
Okay. So basically, when we hear Maghrib, inshallah, we're going to break for prayer, inshallah, for 15 minutes. Now we're going to start with the same code that we had from last time. Now I'm going to call it lic10 add. The first thing we should do is basically divide the data, basically. One very important thing, I like everything to be, as I told you last time, let's just leave this, it's okay, because if you want to draw the data, it's good to have that. Basically, keep that notion of having basically everything in the data here, or basically the parameters of the data are estimated. So the size of the data set here would be estimated so that we don't really have to hard code the number of images, for example. Because if you use another data set, you're definitely almost guaranteed to have a different data size. So if you hard code the data size, the number of images in the data set, you're likely to have to change a lot of things in your code in order for this code to work with another data set. So now we know that the number of images is n images, and the size of the ROI is whatever we have here. So what we're going to do is basically, I think here we already reshaped the NROI. I don't want to do that actually. Probably I'll get a copy of NROI first. Let's just make it NROI original. Okay, that's fine. We don't really worry about that for now. What we have to do now is to have a certain number of n learning. Let's just call it n learn. Okay, n learn is basically going to be the number of learning cases. Okay, and basically we have to have n test. Let's just call it n test is equal to whatever number of testing cases. Okay, if I wanted to have n learn equal to, for example, half of the number of images, for example, this would work. Should I put here n images over 2 also, or what? What should I put here in n test? What should I put here? Is that correct? Actually, I don't recommend that you do that, okay? For the following reason. First of all, if I wanted to have 70% and 30% here, okay? This is not a good idea to have something that looks like this. Why? Because basically the number of images, if I put 3 here, for example, if I took third the data, then there might be a problem. It might be a fraction here. We don't want to have fractions here. So first of all, we have to have round here in order for us to be sure exactly whatever we put here, we'll have a round figure here, we have an integer here. And also here, instead of having an equation also for n test, basically we know that n learn plus n test is equal to n images. The number of images, I'm dividing the number of images into 2 sets. If I decide the first set is equal to this number, then basically the other one would be n images minus n learn, right? Basically, these very minor things actually can annoy you a lot if you don't do them right. Okay, you will see that. We'll see that in a second. Okay. Basically, now we have n learn and n test. Okay. The second thing is let's just keep these like this. What I need to do is I need to divide the NROI. I need to divide the regions of interest into 2 sets now, learning and testing. Okay, so basically I have to have, for example, NROI learn, NROI test, right? And basically have the same thing for AROI learn and AROI test. NROI learn would be equal to what? NROI of, basically the first dimension is the number of images. So basically I'm going to start from 1 to n learn and all. Is that correct? Is that correct? Be correct, right? How about this one here? How about this one here? What should it be? I took the first n learn points as the learning phase or the learning date. I need the remaining images to be what? To be in the testing date, right? So basically, since I stop here at n learn, image number n learn, I should start here with n learn plus 1 until what? Until n images. Right? I should do exactly the same thing in the other ones here. Here, all I have to do is just have ARY and ARY. Now I divide my data into, basically I have normal and abnormal. These were already divided like this in the data itself. I divided each one of the normal and abnormal into training and testing. This way. Okay? What I need to do is to do everything I did here, everything I did for the whole set in ROI, I need to do it for each one of these. Okay? So basically, we need to change a lot of things. Basically, because everything is in ROI, I have to change that into in ROI. If I have learn first, learn, and this is learn. Okay, and I actually have to have another one like this. Let's call it 2, feature 2, n feature 2, and I have to have the testing data then here. Okay, just have to compute the features for each one of them. Okay, now I have to basically, after I do that, I have to combine all of them. Let's do the basically compute these first. Just modify whatever we have here to have all the features, and then see how we're going to combine these features. See what I'm doing? Is it clear to you? Is it clear what I'm doing here? You have any questions about what I'm doing here?
Doctor? According to maybe in the second or in the standard deviation, maybe there is an overrating over the previous feature. Is that true or not?
No, yes, that's true. That's why we're going to, basically what we had at the end here, what we drew at the end here is basically the last one, the last feature. That's why we need to basically have another variable to put all these features or accumulate all these features in. Okay? So this is what we're going to do now.
Okay.
Okay, let's just compute the features first, and then after we do that, we're going to basically accumulate them in one place, in one feature vector or feature variable that will be basically an accumulation of all of these. Okay, let's do it right now. Actually, it's very simple. Let's define a feature space for let's just call feat n as the feature basically feature variable for all normals and abnormals. But actually, you have to have we have L here, learning. And we need to have also variables for testing data. So here in the first one here, all we have to do is just make it like feature L n is equal to whatever we have from here. Feet 1 n. So is that correct? So now I have these variables. Basically, these are defined variables, accumulate all features. So now for after the first feature, I already have the first feature here. So basically, when I overwrite here, basically I overwrote basically the variables, but actually they are still the mean is still here. What I need to do is accumulate here after the second feature. I need to accumulate the second features with the first. I don't need to overwrite it. I cannot write it like this. I have to actually write it in a different way. Okay, so here, after I compute the standard deviation, I actually have to accumulate this with that. Okay, so let us see how we're going to do that. It's just for now, I'm going to actually we can leave it. For the standard deviation, before we do that, let us see the variables we have. Okay, we have a problem. Okay, basically we changed the length of the vectors. So basically here I have to change when I draw. It's not an images anymore. Now it's in learn, right? So basically I use the smaller number for the training set. And basically what I'm drawing here is I'm drawing the learning data only, because basically I assume that I don't have the testing data. To be able to visualize the testing data during the design of the system. So basically I'm just going to read the places where the drawing was based on the number of images and basically put it as in learn. Okay, it should work like this. Okay, didn't work. Okay, we missed one. Okay. Okay. We missed learn feature 1A. Let's see. 1 times 72. Okay, this is not correct. Times 72 is not correct. This is for line 77 here. Oh, okay, because basically we're computing using NRY here. Okay, so basically this has to be changed. Let's just about this part for now. Let's just make it appear for now, just F0. So that I don't have to worry about it until I change it. So now the feet 1A, feet 1N, the dimensions are 1 times 36. The accumulation feature vector or feature variable basically have also 1 and 36. If we want the outcome, if I add this feature, the second feature to the first, should this be 2 times 36 or 1 times 72? What is the first dimension? What is the second dimension in these vectors?
2 by 36, I think.
Right, right, because 36 is the number of cases. What I need to do, instead of having here, for each case, I have one feature, I need for each case in the accumulative variables here, I need to have, for each one of these, for each one of the 36 cases, I need to have 2 features. So basically, I have to concatenate these vectors accordingly. Okay. Remember, if we wanted to add two vectors, let me just show it to you. Maybe x1 is equal to 1 to 4, and x2 is equal to, for example, 6 to 9. Okay, I wanted basically the size of x1, and x2. X1 is 1 by 4, and this is 1 by 4. If I wanted to have x1 semicolon x2, does that look right? Actually, it looks okay, because basically for each one of these, basically, you had only one row, you had now two rows, right? If I added them like this, instead of semicolon, you're gonna end up like this. What I have, for each one of the feature, I have a vector that looks like this. I need to add them to, or concatenate them together in order for me to have the same number of columns, but the number of rows will be concatenated, will be added. Basically, I'm increasing the number of rows, adding a row to the vector that I have. Okay, so basically what I should do here is, let's make it general from the first one. The first one here, I have an empty vector here. So basically, if I make it like this, L n semicolon this. Basically, I'm adding a row to this variable here. If this variable is empty, then this will be the first row. Let me try it here also. It's L learning abnormal. This. Feed learning normal testing normal. We're going to see the variables. After we do that, we're going to see that whenever we add a feature, we basically find that this vector becomes basically the number of rows will grow with the number of features that we add. Here, heat test A. And basically, I'm going to take that and copy it everywhere, basically. Here. Okay. If I do that, basically, let's see what the outcome will be like. See now, feature learning abnormal, now it's 2 by 36. Now, normal is the same thing. Testing, same thing. So this is working. This is the right way of concatenating things. So each time I compute one of the variables here, each one of computer, one of the features, I just concatenated, just added. So basically, I'm just going to take that and add it at the end of each one of the features. Here, the minimum, the maximum also. The median, the skewness, the kurtosis, the percentiles. Then we're going to change. I already removed the if, and I'm going to change the maximum, minimum, all the other features. Going to change it the same way I change the other ones. So now here it's going to be NROI learn, NROI learn. What I'm doing, is it clear for you what I'm doing, or do you have any problems? If you have any questions, please let me know. Now, all the features that I computed so far do exactly what we were doing before. Basically, we're just gonna add a feature to the feature vector. Add a row. How many features? So many features. Okay, we're almost there. I'm sorry, it's very boring, but this is how coding is. That we're going to modify a lot of things. It doesn't really, there is no automated way to do it. Just the percentiles. Okay. The percentiles actually, it will compute several features, not just one. But it's okay. It'll be exactly the same. That's the features here, I think, will have an issue because I think the features here will be, the dimensions of the features here will be different. But let's try it like this. Right now, we accumulated everything in this vector here, but I doubt that we have to probably put a transpose here, but let's try it first and give us an error, likely. Yes. Yes, it's, yes, here it's maybe feat 1n, we're going to find it to be a little bit different. Feat 1n now is 36 times 7. It should be 7 times 36. So in the way we compute the percentiles, it comes out with basically transposed, basically. So what I need to do here is just put a transpose here. I'm not sure we have all of it. Okay. Because basically here we tested feat 1n and feat 1a. Actually, what I need to do now is compute the feat ln. So that I can have all the features. Feat la. Okay, because right now, if you see here, feat LA, it now has 14 features. Here, 14 features. Okay, so I need to test these right now. And as you see now, for the testing data, I already computed the same number of features. So basically, we have the same number of features computed for both the learning and testing data. Here we computed only 1, 2, 3, 4, 5, 6, 7 features because basically it's the last one. I was just computing the t-test for the percentiles because it's the last one that basically filled out feat 1n and feat 1a. When I use this now, I expect to have 14 features. And basically the results for 14 features will appear here. Okay, so let's see that. See now? You have 21 now, because basically we have 21 features. Okay? The 21 features we accumulated here in feet LA and feet LN. Actually, we did it, yes, it's done in the improper way. Basically, we have to transpose that. Because now it did the t-testing along the 36, not along the features. Okay, we need to do it in the other way. So basically, we have to transpose that and that. Okay, that we need to have 14 values, 14 p-values for each one of the 14 features, not 36 values for each one of the cases. We do not test the cases. Basically, we're not comparing the significance of the cases. We're comparing the significance of the features. So now I have 14 p-values. See here we have 0.17. This is insignificant. This is above 0.05. Here also we have 0.6. So this is not good. So basically, among the 14 features that we computed, we have 2 features that basically the H0 or the null hypothesis was the correct one. Or basically these features are not useful. So we need to remove them. How can we remove them? How can we remove these features? How can we remove a certain feature from an array? So now we have 14 times 36. I need the array elements of 1 here for all cases, and of 2 here or for all cases, and 1, 2, 3, 4, 5, 6, 7. Number 7, also I have to remove it. There's a very simple way of doing that. Basically, if I compare the p-value, greater than 0.05. Sorry. P here, small p. Yes, p greater than 0.05. Now it has 1 in the dimensions that are basically not useful. A very easy way of removing these from the array is basically if we have, for example, feet L n, for example, of p greater than 0.05 is equal to empty. By doing this, all the features that have 1s here will be removed. So now see now the feature L n has a dimension of 14 times 36. If I do this very simple statement, see now, where is it? Okay, it didn't actually shouldn't have done it like this. Maybe I should do it with A first. Actually, this 2-dimensional array, so basically I need to remove the first array only, the first dimension only. So I should put that in the first dimension and the second dimension as is. If I do it like this, feature LA is now 14 times 36. Now it's 12 times 36. So in order for me to remove useless features, I have to do it this way. So basically what I should do is just copy the same exact statement I have here. Should remove it from both the testing and the learning, because basically I need the same dimensions in both. If I found the features to be useless from the learning data, I should remove it from the testing data, because basically I determine which features to be used from the learning data, and then I compute them for the testing data when they come. So basically I have here L n, and this is n. After I do that, if I test again, find that all features will be significant. Let's try it. See now, all the features now are significant, as you see here. Okay, if you look at this, this is 0.17, but actually it's times 10 to the minus 8. This is a very small number, actually. Okay, so now what we did is to have an array with the features. We have now whatever it takes, whatever we need to start doing the classification. Okay, so this is exactly what we're going to do after the break, inshallah. Okay, let's have a prayer break for 15 minutes, and we will meet again at 6:15, inshallah. Okay. All we need to do is just, I'm going to show you how to do the classification using just two statements, two lines. That's it. Okay. So let's take a break now for 15 minutes and come back, inshallah. Okay. Just gonna write down here so that you know. See you inshallah then. Assalamu alaikum.
Five.
Are you all back?
Yes.
تقبل Allah. Let's get started. Now we need to basically explore the classifiers that are built in MATLAB. So basically the easiest way is just go to help here and search for classification. Just classification, okay? You will find so many different things. If here support vector machine classification, let's search for the just classification and see exactly. I think this is probably the naive Bayes. There are so many different things here. So let's start with just here, support vector machine classification. Or here, classification is the binary and multi-class problems. This is probably the classification that basically, let's start with the nearest neighbor. Here you have different classification. You have something called classification trees, discriminant analysis, naive Bayes, nearest neighbor. Let's start with the support vector machines. So many different things. Let's start with the nearest neighbor classifier, which is basically the simplest way. Basically, the first thing is to create the nearest neighbor model. There's a very simple function called fit KNN, which is basically, this is a function that builds the KNN model, basically. Okay, I don't see any examples here, but let's just get to that. Maybe I should open that in a new tab. And then in order for us to classify observations, basically the test cases are called observations. You basically build the model and basically use this model to classify observations or test cases. Okay, so the function that we're going to use here is just predict. Let's see how fit KNN works. Okay, basically give the data your x and y here. Basic x and y is basic x is the feature space vector. It's the one that we just built. For each case, you have a set of features. And the y's are the basically the labels. Okay, each one has a certain label. Okay, so for example, here you have at KNN, the input, the output, the features for the cases at the training cases we have, the labels for the training cases, and you have certain parameters here like the number of neighbors. You can choose it here as 1, 2, 3, whatever. And basically use it as is. Basically, we're just going to copy that and include it here. The important thing here is notice that we have one for, let's just remove the standardizer. We don't really need it for now. And let's just call this model 1. And basically, I'm just going to build different models. Maybe maybe I'll just use 1, 2, 3, and basically I'm going to change the number of neighbors for each. You can change it the way you want, by the way. I'm just going to build different models and basically predict based on that. But the point is we don't have X and Y. In X and Y, we don't really know which ones are X and Y. Basically, X here should be the features, okay? Y should be the labels, okay? The thing is, X should have a mixture of normal and abnormal cases. So basically, whatever I have here for learning, for the normal and abnormal, I should have both of them as one vector as the input to my classifier learning here. Let me show it to you here first. Basically, what I have right now, I have a vector for the features. Maybe I should write it a bit different. I have here cases. Each one is a case, okay? And here you have features, okay? I have that for a vector like that for learning, or basically for the normal. I have a vector like that for the abnormal. The same dimensions, or maybe they might be different, it doesn't matter. Okay, so I have features for the normal and abnormal. Here, the number of cases here, we had 36. The number of features, I think the last number we had after we removed the features that were not useful was 12. So basically this, for the normal we have 36 by 12. Or actually it's 12 by 36. This is what we had. 12 by 36 was kind of transpose. Here, we have also 12 by 36. If you combine these, we'd like to have one vector that has 36 cases, actually 36 plus 36 cases,